All right, so here we are now talking about inverse trig functions integration. So today we're going to look at just what the formulas are for integration, and um, and then we're going to double check and make sure those formulas work because they're a little different than the derivative formulas I gave you. We'll do some quick, easy problems just to get our feet wet using the formulas. And a little reminder about how you know when U sub can be used, because like I was talking in class, one of the hard parts about this is going to be knowing when to use different techniques, because problems can look similar but not be inverse trig functions. Then I'll give you a few problems to try. We'll go over the solutions to them. There's going to be some more problems to try. These are going to be more complicated, and we'll go through those solutions and then just some final thoughts. Now, if you are going to skip around in this video, the items that I've starred are the ones that I recommend, and the bookmarks, remember, are in the description, but obviously you need to know what the formulas are. Try the quick examples to get your feet wet, so that's why those are starred here. And I definitely recommend looking at the more examples because these have some tricks in them, and then just some final thoughts. So that would be where I would at least do those things. Okay, let's get started. So these were our derivative formulas that we did last class. And yes, you could just, go backwards and say that this integral is equal to this and so on. But that's only useful when you have just simple x's here. So there's actually some variations of these formulas that we're going to use for integration, which I think are a lot more useful to use and make things a lot easier. So these are the formulas. And so if you want to pause the video, definitely pause the video and write these down. I just want to point out a few things on them. So a is greater than 0, so this a is a constant, and the constant is a positive constant. Um, and yeah, I know it looks like I may have forgotten something, because if you look at arctan and arcsecant, these both have a coefficient of 1 over a in front. Arcsine does not, and that is not an accident. This one really does not have that coefficient, so that's a little weird. Notice also, I'm going to go back up to the derivative formulas really quickly. Notice for the derivative formulas for arcsecant, that had an absolute value here, but we are not putting an absolute value here. We're putting it over here. And again, I'm going to show you that it really does work. So these are the formulas, and our goal is going to be trying to turn a given problem into one of these forms so we can identify what U and A are, and then we'll be able to just plug into this side of the formula. Also make sure, notice that each numerator is du. You need whatever you decide is u, the derivative must be on top. So keep all that in mind. Now, this next page, if you want to skip over it, you feel free. Honestly, this is not that important, but I did want to show that it really does work. Like, yeah, there's no 1 over a, even though you may be tempted to put it here for arcsine, there is none. That even though the absolute value is here, it's going to, for arcsecant, this is going to work. So anyway, on the next page, I have taken the derivative of this to show you get here. I've taken the derivative of this to show you get here, and I've taken the derivative of this to show you get here. And so the derivatives are each step of the way. Because here we are taking the derivative of something with an absolute value, this is the formula for how you take the derivative of the absolute value of a function of x. And so you can see this one becomes a little more complicated using that. But anyway, you can skip this if you want. Okay, so now let's do a quick few examples to get our feet wet. Now I have the formulas up here in small font just to kind of remind us what they are. But see if we can first just identify which of these three formulas you're going to use on which one of these. And I would encourage you pause the video and try to figure out, does this go for this one, or this one, or this one, and so on. Just try to figure it out. Okay, so hopefully you did pause the video. Some things to look for. I mean, obviously arctan doesn't have a square root. So, and it's got to have a plus sign here. And this one doesn't have a square root. And it has a plus sign. Yeah, I'd say this is a safe bet that this one will go here. Now, when you're focusing on whether to use arcsecant or arcsine, it is tempting to focus on what is out here, but do not focus on that. There are times when you might have something here, but it actually is an arcsine problem. Or maybe you don't have something there and it ends up still being an arcsecant. And it can happen. It seems weird, but we'll see that, and you'll also see it in your homework. The thing to focus on is under the radical. Is it the variable minus the constant, or is it the constant minus the variable? So if you look at this first one, it is the constant minus the variable. So this is your arcsine. The third example is the variable minus the constant. So that's arcsecant. So I'm just going to go ahead and quickly rearrange these, put their applicable formula up above, and then I'll show you how to use them. Okay, so like I said, these are some quick and dirty ones. They're pretty straightforward. When you are doing these, you're going to want to identify A and U, and then make sure you have du in the numerator. So now that we know constant minus the variable in a square root is going to be arcsine, now we want to find A and U. So we can see that A squared is 9, so that means A is 3. And then U squared is x squared, so we can see that U is x, and that would make du equal to dx. So now let's go ahead and replace everything in here. Now I have the dx off to the side, but remember that can get multiplied in the numerator. So 1 times dx is the same thing as 1 times du. So that does put du in the numerator. The 9 can be written as a squared. The x squared can be written as u squared. And then we have the minus and the square root. So 9 is a squared, x is u squared. Hey, look, it's a perfect match for our formula. So now we know the answer is going to look like this. The answer is going to look like arc sine u over a plus c. Substituting in, u is x, a is 3. There's our answer. So at any point, if you want to pause the video and kind of chew on what's going on, definitely do it. But there's a first example. Second example. So we, excuse me, we've decided that this is going to be an arctan problem. So the same thing, we want to identify a and u. So if a squared is 5, then a is the square root of 5. If u squared is x squared, then u is x, and that makes du dx. So let's go ahead and see what happens when we plug in. So du is dx, so that dx on top will become a du. 5 is the same thing as a squared. X squared is the same thing as u squared. And again, we did it. We have a perfect match for this. So there's our answer right there. 1 over a arctan u over a plus c. And if we substitute the a's and the u's in, we get 1 over root 5 arctan x over root 5 plus c. And there you go. All right, let's do the last one. So we've determined that this was arcsecant because it was the variable minus the constant, so we know it's arcsecant. U squared is 4x squared, so the square root of that will be 2x. That means du is 2 dx. Don't forget the du's and dx's, those are important. A squared is 7, so a is the square root of 7. So let's see what happens when we plug in here. So we only have a dx in the numerator, not a 2dx. We really wanted that 2 there. Huh. The other problem is we need a u on the outside. We only have an x, which is not the same thing as u. Now think about how we can fix this, and some of you guys might see it. One thing we can do, we want du in the numerator, so to get du in the numerator, I need 2dx in the numerator, so I can put a 2 up there. And in the past, we've made up for it by putting a 1/2 on the outside, but conveniently, and this will often happen with arcsecant, we also want a u out there, and u is 2x. It's only x right now. We can put a 2 right there as well. And that fixes the problem for us. We have du in the numerator. We have u on the outside of the radical. So we have du in the top. We have u on the outside. And on the inside of the radical, we have u squared minus a squared. And now we have a perfect match right there. So that is something that you got to watch out with arcsecant. You need to make sure that this is u. But a lot of times, not all the time though, so you do have to be careful about this, but a lot of times you can fix that problem by putting whatever coefficient is missing up here as well. And it will also give you the du in the numerator. But now filling into the formula, we know the answer would be 1 over a, arcsecant absolute value of u over a plus c, and plugging in our values, we have 1 over the square root of 7, arcsecant absolute value of 2x over root 7 plus c. And a little something, I'm not rationalizing my denominators. You don't have to know how to do it. We can take that 2 out of the absolute value and write it like this. You still need the absolute value though, so is it more simplified to write it this way? I wouldn't call it more simplified. We often will do it, but we also sometimes don't. It's just, I don't know, maybe it's a mood thing. Anyway, just know that you can. So when you see this on a multiple choice test, that could be an answer. Okay, so there's some quick ones just to kind of get our feet wet. So a little reminder of something to look for. If you just kind of take a second to look at these two problems, they're very similar, but they're not identical. Do you see the difference? The second one has an x in the numerator that the first one is missing. Does that affect how to do the problem? And the answer is yes. Think about how you would solve each one of these integrals. Hopefully, you were thinking for the first one, oh, hey, that's exactly the arctan formula because it's exactly the arctan formula. This is arctan x plus c. Well, what about the other one? Well, the thing to notice on the other one is we have the derivative of the bottom in the top. I mean, we're off by the 2, but the derivative of the bottom would be 2x. I can make up for that by doing this. Now I have the derivative of the bottom in the top. That's a natural log problem. This is just 1/2 natural log of the absolute value of the bottom. And for this particular problem, 1 plus x squared is always positive. So you could write it like this, or even you could make that 1/2 a square root and write it like this. So you get totally different looking answers, even though the original integral looked very similar. So be on the lookout. If you have the derivative of the bottom and the top, that's natural log, and you can use u sub, let u equal the bottom. So du is 2x dx. So 1/2 du is dx. And when you do u sub, you would wind up with 1/2 times the integral of du over u, which is 1/2 natural log of u plus c, which does get us back to exactly where we were. This was just the quick way of doing it. If you can just put the derivative of the bottom and the top by fixing it with a constant, multiplying by a constant, you can do it. So keep that in mind. Look for derivatives of inside functions or derivatives of denominators. If it's elsewhere in the problem, it's not an inverse trig. Okay, so here's some examples for you to try. I encourage you to pause the video and try these on your own and keep in mind what we were just talking about. And then we'll take a look at the solutions. Okay, here's the solution to number 1. So the thing to spot here, actually, let me go back to the original just so we can see it. We did not have the derivative of the bottom and the top. The derivative of the bottom would be 18x. Sure, we could multiply 4 by something to get 18, but we don't have an x, and you can't fix it by multiplying by a variable. That is incorrect. It has to be a constant. But we do have a plus sign in the denominator. That we can turn this, if it's a constant over something with a plus sign and no radicals like the other two, that's arctan. So here's just a reminder of what the arctan formula is. So a is 1, u is the square root of 9x squared, which is 3x. Du would be 3dx then. And so I wanted to put a 3 on the top so I could have it, so I put a 1/3 on the outside to make up for that. That would bring me with 4/3 on the outside, and then 3dx is du, and then a squared plus u squared right down there, which filling in the formula and then filling in for a and u, we end up getting here. So take a look at that one. Again, pause the video at any time you feel you need to. Okay, example 2. So here's example 2. I see a composition. I do not have the derivative of the inside elsewhere in the problem. The derivative of the inside would be negative 2x. Sure, I could put a negative 2, but I can't make up with a variable, so this is not going to be a u sub problem, but I do have a square root in the bottom with a constant minus a variable. That's arcsine. And here's the arcsine formula. So a squared is 4, so a is 2. U squared is x squared, so u is x. If u equals x, that means du is dx. So filling in, we get this. Now notice, I'm in terms of u, not in terms of x anymore. I've left off the limits of integration. I'm going to put this thing back in terms of x before I put the limits back on. So now I can go ahead and use the formula just from here and fill in my u and a. And now that I'm back in terms of x, I put the limits back on. And then it is a definite integral, so I plug in a 1, I get this. I plug in a 0, I get that. Arcsine of 1/2 is pi over 6. Arcsine of 0 is 0. Your answer is pi over 6. There's example 2. All right, example 3. Now, you may have been thinking arcsine, because we have in the bottom, we have a constant minus a variable, and so you may be thinking about doing that. A would be 1, u would be x, so that would make du dx. what the heck do we do with this thing then? Well, the answer is we don't. This is not the way to approach it. Remember, another thing is if you see the derivative of part of the problem elsewhere in the problem, it is a u sub problem. And the derivative of arc cosine x is 1 over the square root of 1 minus x squared. We have that right there. So let's try this again. If we do u sub and let u equal arc cosine x, then du is this. Don't forget it's got the negative. I just don't have the negative, so I moved it over here. And then this one I'm going to go ahead and leave in terms of u. So this is me changing the limits of integration. But when you plug in, arc cosine x turns into u, 1 over the square root dx. 1 over the square root dx turns into negative du. And then here's my new limits. And now you can see this is a much easier thing to integrate. So this is why it's going to be important that you have those formulas memorized so you can recognize that the derivative of this is in the problem. Otherwise, you're not going to see it. Anyway, I'm just finishing it up here. You can see my work there. And there's your answer there. Okay. Let's see what's next. Here's some more examples for you to try. And I'm just giving you some hints. They're tricky though. There are some things that come up here. With example 5, a hint here, and we'll talk about more when we go through the solution, you will somehow have to split this into 2 integrals. But this one is definitely a challenge. For example 6, when you have a rational function for your integrand, if the degree of the numerator is not smaller than the degree of the bottom, you have to divide first. Even when the degrees are the same, you still have to divide. So this is going to be a long division problem first, and then you can try to integrate. So try those, but they are not easy. So you think about them though before you look at the solutions. All right, here's the solution to the first one. So here's the thought process. We first have to decide if this really is inverse trig, if that's a good way to approach it. And I do see a composition, but the derivative of the inside would be 2e to the 2x. And I don't have that anywhere in the problem. I just have a dx. So it's probably not a u sub problem. But what I do have instead is a square root in the bottom with a variable minus a constant. And notice there's nothing outside here, like is in the arcsecant. I'm not looking at that. I'm just looking at the variable minus the constant. This is making me think arcsecant. So let's see where this takes us. A squared is 1, so a is 1. U squared is e to the 2x, so u is e to the x. And that would make du equal to e to the x dx. Now, I don't have an e to the x in the top, but I can put one in the top as long as I put one in the bottom. And I can do this with a variable as long as I keep everything inside. As long as I don't try to do something on the outside of the integral, that would be bad. But on the inside of the integral, that's good. So if I put an e to the x at the top to give me du, I have to put one in the bottom to make up for it. But that worked out nicely because I do need a u on the outside of the integral, or the radical, I mean, and that would actually get me my u. So this ends up being the trick. There's my du in the top, my u on the outside of the radical, and u squared minus a squared on the inside of the radical. And now it's a perfect match. So I just fill in the formula. Notice I'm keeping the absolute value, except e to the x is always positive, so for my final answer, I can take it off. And there's my answer. If you need to pause it to look at this, go ahead, because like I said, it gets tricky. But there's this first example. Okay, let's look at the next one. So here's example 5. Now, example 5 also gets pretty tricky. So the derivative of the inside of the radical would be negative 8x. I have an x. I mean, I could put negative 8 here, and that would be okay. But then I have this 3. What do I do with the 3? Dang it. And if this x wasn't there, then I would be okay, because I could treat this like constant minus variable and make it an arcsine problem. So we split it up. If you have the variable, or sorry, the derivative of the inside in the numerator, but then you have an extra term, try splitting up the integral and see what happens. So that's what I did here in blue, was I first split up the integrals, and then I do have the derivative of the inside in the top, so I made it a u sub problem. I let u equal the inside function. Here's my du. I didn't have the negative 8. Oh my goodness. So, can you spot my mistake? I need to divide by negative 1/8, or negative 8. So I'm actually going to divide here, and that will not make it negative 16. That's going to make it negative 1/4 on the outside. Good thing we're going through these together. So, there's my u du, and if I go ahead and plug everything in, now it becomes a pretty straightforward integral. Remember, this means u to the negative 1/2. So add 1 to the exponent, it's positive 1/2. Divided by the exponent, it's 2. And then I just replace the u with what it equaled. So that was the first part of the integral. The second one, the second integral that I created, it was a constant over the square root. I went ahead and made this arcsine then. So here's my a, there's my u. This makes du equal to 2 dx. I had a 3, but not a 2. So I multiplied by 2, and then I can divide by 2 on the outside. And then putting it in terms of u and a, I get this. And this is a perfect match for the formula. So I just plugged into the formula, and there's the second part. Make sure you put your answers together into one answer like this. So be on the lookout. Sometimes you have to go ahead and split them up like this. Okay, last one. So first of all, the degree of the top is bigger than the bottom. So I did have to do some long division here. And after I did long division, I got this. So I rewrote this integrand as this right here. And then it was much easier to integrate. Integral of this using power rule, integral of 1, integral of this is arctan, you get your answer. So there's those. All right. So now, actually, let me go through this really quickly, this long division. When you're doing long division, if you have any missing terms, make sure that you put placeholders for those. So that's why I have all these zeros. If you have missing terms in the divisor, it's actually not a big deal. You don't need the placeholders there. But for the dividend, the thing on top, any missing terms, you need a 0. And then as you do the work here, notice I was lining up all like terms. So all the x to the 4th were in this column. Everything that was x cubed was here. Everything that was x squared here. Everything that was x. Everything that was constant. And then look at just the first term. You're dividing, or you can also think of it as what do you multiply by x squared to get x to the 4th? And that's x squared. So multiply x squared by each one of these, and you get x to the fourth plus x squared, but then you have to subtract it. And if you've done it right, these first terms should always cancel. But then subtract everything else. So 0x cubed minus nothing is 0x cubed. 0x squared minus x squared is negative x squared. 0x minus, or sorry, I just brought this down. My bad. And then I did it again. What do I multiply by x squared to get 0x cubed? And that was 0x. And then you multiply, subtract, bring down. And do it again. What do you multiply by x squared to get negative x squared? Why, that would be a negative 1. And then you multiply, you subtract. And in this case, there's nothing left to bring down, so you know you're done. And this is your quotient, x squared minus 1. So that's where that came from. This is the remainder, minus 1 over the divisor. So there's that. Okay. So just some final thoughts. First of all, just take a look at these three. They are very similar. See if you can figure out how to integrate these. What strategy would you use? All right. If we look at this first one, the derivative of the inside is 2x. Now we have an x here, but the problem is the x is in the bottom. So that don't think of this as an x. Think of it as 1 over x. So that's not really the derivative of the inside. So we can't do that. Well, we do have the variable minus the constant, and the variable, that would make u equal to x. That would make a equal to 1. That would make du dx. Everything does match here. There's our u on the outside that we need for arcsecant. There's our u squared minus a squared we need inside the radical. There's our du in the top. This is an arcsecant problem. Now, if you look at this one, this time we do have the derivative of the bottom, or the derivative of the inside elsewhere in the problem. If we let u equal x squared minus 1, du is 2x dx. All I need to do is move this 1/2 over, and there's that derivative of the bottom, or sorry, the derivative of the inside in the problem. So this is a u-sub problem. Now over here on this last one, again, it's not a u-sub problem because the derivative of the inside is not elsewhere in the problem. We would need an x as we saw over here. I maybe, if I want to think of it as an arcsecant because it's variable minus constant, that might be tempting, but we can see over here, we don't have an x out here. And even if we try to make up for it and put an x, I'd need to put an x up there, and that would cause problems. So that's not going to work. This one, we have no formula or strategy yet. And we won't this year. We won't see problems like that this year. You'll be able to deal with this in future years, but not this year. So this one we can't do. Okay. Last thing is try looking at these. Same thing. See if you can figure out what method to use. All right, if we take a look. So these are definitely not inverse trig. I mean, they don't even have plus or minus signs in them. It's not even inverse trig. But let's take a look. I see a natural log of x here. And we know the derivative of the natural log of x is 1 over x. which I have right here. It's a u-sub problem. We're going to let u equal natural log x. Let's just finish this up and see what happens. That means du is 1 over x dx. So 1 over x dx, that's du. That's going to put du in the top. I still have a natural log of x in the bottom, but that's u. So it becomes the natural log of the absolute value of u, which is the natural log of the natural log of x. So that's this first one. It's a u-sub problem. Look at the second one. The second one's the same thing. If we look at part of the problem, we can see its derivative elsewhere in the problem. It's still a u-sub problem. If we let du equal the natural log of x, or sorry, u equal natural log of x, du is 1 over x dx. And so this would become the integral of u du, which is 1/2 u squared plus c, which would be 1/2 natural log of x squared plus c. This one, I don't, what do? If I let u equal natural log of x, I don't have its derivative. I don't have 1 over x anywhere in the problem. Again, this is one that we don't have a strategy yet. And we won't. This year we won't be doing it. This one, by the way, if you're curious, uses a strategy called integration by parts, but that's a BC topic. That's not an AB topic. So we won't be doing it this year. And if I go back up here, this problem, this is actually uses something called trig substitution. That's not even a BC topic. We won't be doing that. So that's the end of the lesson. Oh, actually, here's just some things to keep in mind. Don't forget, if the integrand is improper, if the degree of the top is not smaller than the bottom, you must divide first. Always, always, always divide first. Is the derivative of the bottom and the top? It's a natural log problem. Let u equal the bottom and you'll see it. If you have a composition, is the derivative of the inside equal or elsewhere in the problem, then you're going to use u sub. So be on the lookout for that. All right, so those are some things. And yeah, have fun with the homework. All right, I'll talk to you guys later. Bye.